잘못 했네. 답을 잘못 써놨네. 아, 그건 아니네. 근데 원래 우리는 이걸로 아까 말한 거였는데 우리는 왜 쓰기 되게 굉장히 실수했는데 굉장히 사랑합니다. 잊지 말려는 알고리즘을 써야 된다고 생각했는데 맞네. 그래가지고 뜻을 두고 알킬 하나 더 들어가고 알고리즘 맞네. 오케이. 많이 맞췄네. 우리 많이 안 배웠는데도 불구하고 식물반도 배우는데 시험도 일반대 조금 배우기 시작했는데 양이 좀 많아졌어요. 시험 볼 때 시험 문제 주고 그걸 다 풀지 않을까 그랬는데 채점을 하려고 그랬다 보니까 나도 잘 모르겠는데 헷갈리는데 이런 것들이 안 보이더라고요. 그러니까 여러분들이 따로따로 배웠던 걸 한꺼번에 모아서 보는 게 한눈에 안 들어오는 거 당연한 거예요. 그러니까 계속 보면서 큰 그림을 놓치지 않으려고 노력하면 계속 쫓아올 수 있어요. 자, 그래서 몇 가지 복잡한 반응들이 나오고 릴레이션도 나와서 오늘 점검을 해보는 거니까 알코올에서 알데하이드로 스탑시킬 때는 데스모틴이고 끝까지 보내면 더 스트롱한 거 그럼 더 시아베스리나 퍼마가네이트나 이런 거 스트롱한 거 쓰면 되지. 지난 시간에 처음 배웠던 게 다이버리라는 거 배웠고 다이버스면은 에스트에서 알데하이드까지 가는 반응을 스탑시킬 수도 있어요. 저것도 푸시하면 알코올까지 가. 그런데 온도 낮추고 잘 조절하면 알데하이드에서 스탑시킬 수도 있었어요. 그 정도까지 배웠고 다음 문제는 조부님이 냈는데 조부님 이걸 보자 그러더라고요. 오케이. 그래서 여러분들 답변에 따라서 세영이가 오늘 세영이 대한 거 처음 아니야? 세영이 처음 아니야? 축하한다. 오케이. 자, 이걸 바탕으로 그래서 어느 파일을 될까 생각을 했는데 이 파일을 볼게요. 자, 오늘 수업 노트를 안 올려줬는데 대부분 수업 내용은 지난 시간에 많이 못한 게 많아가지고 이거 쓰고 뒤에 약간 추가된 거는 나중에 수업 끝나고 올려줄게. 내용을 어떻게 마무리를 할지 몰라서. Okay, let's start today's lecture from here. So in the last class, we had a ketone, and if you had an amine, that amine attack first, and then dehydration occurs, and depending on whether it's a primary amine, then it forms CO double bond is exchanged with the CN double bond. That's what we call imine. Right? And then the enol form of that we call enamine, and enamine is more preferred when this is the secondary amine, because if there is the imine form, it should be positive charge here. So to remove that positive charge, it prefers to go to the enamine form. Relationship of these two, tautomerization. So proton is moving, only proton change the isomer we call tautomer. So that's what we have learned. And based on that, further extending this imine formation, Imine is unstable, so it's a reversible reaction back and forth. But if it has one more dihedral atom next to nitrogen, oxygen is a hydroxyamine, and NH2, NH2, what is the name of the reagent? 네, 한두 사람 기억해 주면 좋겠네. 그래야 친구들한테 자극이 될 거 아니에요. 외워야 되나 봐. What is the reagent name of this? Hydrazine. Okay. If you have hydrazine, then similar to the imine, the CN double bond is formed. That product is very stable, named as. Do you know? If you react this with this the carbonium, then what is the product name? This is a hydrazine. If it is added, hydrazone. Okay, it's a hydrazone. If there is a hydroxyamine, if it is added, it's called as a oxine. So it's a oxine. Okay. So the product should be hydrazine, but here, if you add a strong base together, extra reaction happens. If it is not, if it is without the strong the base, it should be hydrazone. But with strong base, further reaction happens. Whole oxygen is removed. Hydrazone intermediate is formed, and whole oxygen is removed like this. Reaction mechanism like this. First step is this hydrazine attack, and then water is removed. So hydrazone is formed as intermediate, and then it's a stable molecule too. Okay, but here if you add strong base. So here, if you have strong base, then this strong base head off this problem, and then push and push, and then nitrogen is released. So and the result is a quite funny reaction. Carbon and CO double bond is there. Totally, the oxygen is removed. So by adding hydrazine as an intermediate, and then using strong base, and then we remove whole oxygen. This reaction is quite unique. Usually we try to attach functionally, but sometimes we want to remove that extra oxygen, and that too. So that reaction is quite reversible. So this kind of a ketone, you can remove this even not at the aromatic IQ aldehyde. Aldehyde ketone is similar properties of hydrazine, and then with the strong base together. So you can remove. Now, this reaction, we learned a similar reaction in terms of hydration. Now we have a CO double bond. CO double bond is charge-wise, electron is pushed into this way. So this is partially negative, partially positive. That's why this CO double bond of 5 electron is not very much nucleophilic, because this oxygen is quite greedily attracted the electron, it's just holding. So nucleophilic is not so high. With CC double bond, they tend to donate the electron. So in this case, this position is positively charged. It can be attacked by different nucleophiles. If it's water is added, 2 hydroxyl, 1 dihydroxyl. If you have 2 hydroxyl, this is what we call diol. And if it's the same position, the water is added there. This is what we call 1,2 diol, 1,1 diol. alcohol comments, and eventually the whole two possible positions can be exchanged by alcohol. Looks a little unstable structure, and this kind of structure we call acetal. Originally we had as a ketal and acetal. If it is the aldehyde and then two alcohol added, then we call acetal. If it's a ketone and added to the alcohol, then we call ketal. But these days it's mixed up. Usually acetal can mean also the acetal is a little more common name than ketal. Anyway, carbonyl group and then two alcohol added. That's acetal. But if you look at here, it's also possible there is one still remained as a hydroxyl, the other one is alcohol. That's kind of a half reaction. But in that case, we call hemiacetal. Hemi means similar to semi or half. So similar to acetal, half acetal. So this is called as intermediate as hemiacetal, and this is acetal. Okay, this is a new term we are learning here. This is called as a gem diol. This is called the fissional diol. cis 다이올이라고 연결하기 좀 이상해서 fissional means it's a neighbor. 1,2 diol is called as a fissional diol, and 1,1 diol is called as a gem diol. So acetal is similar to gem diol, alcohol version. And sometimes, in many cases, looks like it's a little unstable. It's not very stable structure. Okay. And if you think about this conversion, how can you do? Now this reaction is that what type of reaction is this? Reduction, right? And then it seems like we need some hydride reagent. And we have looks like a competing reaction. Ketone is there and ester is there. We learned the two reagents. Lithium aluminum hydride and sodium borohydride. If you add the sodium borohydride here, then what happens? Only this one is reduced into alcohol. Right? Lithium aluminum hydride, stronger one, you can reduce both. Right? Now, your job is you wanted to reduce only less reactive one, keeping the original one on the intact. So we have seen this kind of a similar situation before, right? If you have a more reactive one, you wanted to attack only the other side, and what is your strategy? Protecting group. Okay. So for the protecting group, you have the previously what we have learned was a TMS, trimethyl silyl group to protect the hydroxyl group. That's what we have learned. Right? And protect hydroxyl, and we could make Grignard reagent into the reaction, and then deprotect. So deprotection was acidic condition, acidic hydrolysis, and protection was basic TMS addition. Now here, usually the ketone is more reactive than ester. So in this case, one option is you can add. This reaction may not be directly can be happening. So you wanted to protect this side. How? By making acetal. So that means if you add excess amount of alcohol that does not attack here, that acetal forming happened only to the ketone, then let's say if you have 2 methanol or excess amount of methanol by removing the water, then you have 1 methanol, the other methanol. That's one way you can do. Reaction condition, acidic condition. To protonate this position and then let the alcohol attack and then make that acetal. Then acetal, it doesn't have a CO double bond to it. It's a CO single bond each, two of them. And it's not electrophilic anymore. That's why next step of reduction it can happen only here. This can be attacked and then can be reduced. But that 2 methanol added acetal is not so stable. To make it more stable, one trick is you can use this kind of connected diol. Then one alcohol attacked, and then the other alcohol is existing nearby, so it can be more easy to attack that position. And then this is acetal forming, but this is cyclic acetal. And then this can be protected this way. Then this position is not electrophilic anymore. Now you can add a strong hydride reagent. Then that hydride reagent can attack this ester position and then reduce this. And then later you can deprotect this. Again, acid condition with the water. Because this reaction is an equilibrium reaction competing between alcohol and water. Right? So to form the acetal, you want to dehydrate, remove water. To put it back into the carbonyl group, you add water in acid condition. To make it more stable acetal, we use this kind of a cyclic bond. Then this product is more stable than 2-methyl acetal. Makes sense, right? So this is the second strategy we are learning: protection of carbonyl with a protected group. Okay. Previously it was alcohol protection. Now this is the carbonyl protection only for aldehyde and ketone. Ester or carboxyl acid doesn't work with this. Okay. So similar reagent, it's almost the same. So previously it was one less carbon, it formed 5-membered ring. In this case, it forms 6-membered ring, almost the same reactions. If you need to protect this group, then either 5-membered ring or 6-membered ring. Acidic condition, dehydrated condition. Okay, then you can protect it. To deprotect, same condition, you just add water. Then first this reaction. Okay. Now that acetal form looks like a little weird and not very familiar to you, but you may know this molecule. Anybody knows the molecule name? Glucose. Yeah, this molecule is the glucose. Glucose usually we draw different forms, like a 6-membered ring like this, or a chair conformation like this. This is glucose. This glucose, if you draw it in different form, open form is like this. If it's a linear form you draw, and this position here, this position looks like there are many hydroxyl here. Carbohydrate means carbon with water, that's carbohydrate. If you draw those molecular formula, that's immediately C plus H2O and 6. That's a carbohydrate, a lot of hydroxyl group around. Looks like this hydroxyl and this hydroxyl is the same. Actually, this hydroxyl is by attack, originally it was aldehyde, this position, and then this was attacked by this hydroxyl group, and it formed this kind of a funny structure. This is one example of hemiacetal. Right? One side is original, other position here, this oxygen, but the other one's attacked, this is alcohol in attack, and then it forms this funny structure. Means this is quite dynamic structure. Stereochemistry wise, it can go up or it can go down. And even not only this hydroxyl can attack too. Then if this hydroxyl attack, it forms 5-membered ring. So glucose, usually this is maybe the most stable, the isoform of the total 5, the isoform. But actually this is highly dynamic mixture of 5 different isomers. Its connectivity is changed, you can call it as an isomer. And this is dynamic isomers. And glucose has this one as most stable, the isomer. But galactose, mannose, similar with the carbohydrate with different stereochemistry, the ratio of 5 isomers are all different because of this funny acetal, hemiacetal formations. Okay. So acetal is commonly one of those most fundamental biological molecule. The first product we make through photosynthesis is glucose. Very first product of biological synthesis, and then this also has this kind of acetal, hemiacetal structures. If I change this OH with R, alkyl group, what would it be? Is that hemiacetal? Is that ketone? That's one more reaction, right? This was originally aldehyde, one alcohol attack, another alcohol attack. If this is OCH3, that is an acetal. This is the same hemiacetal with the one side hydroxyl. 얘기를 다 해줘도 눈에 빨리 안 들어오지. 그래서 눈에 조금 더 익숙해지도록 자주 들여다볼 필요가 있어요. 알코올이 여기서부터 이렇게 쳐가지고 어정쩡한 다이나믹한 인터미디어트 비슷한 아이소모를 만들고 있는데 여전히 5개 중에서 얘가 제일 많아. 그래서 주로 이렇게 그려. 그렇지만 이렇게만 존재하지는 않아. Maybe in high school you have learned something like reducing end. 나중에 되죠. This aldehyde is chemically quite unstable, chemically reactive. That's why the 당뇨병, if you have too much glucose, this generates a chemical trouble. It can make a cross-linking, it can generate a lot of reactions, oxidation reduction reactions. That's why we cannot live without glucose. But if you have too much glucose, because of this aldehyde group, reactive group, it generates a lot of problems. The most representative issue is the 당뇨병. Okay, this is hemiacetal. New reactions. Fittig reaction. Fittig is a chemist's name. Maybe the German chemist. Fittig reaction. Reagent summary is like this. We have the carbonyl group, and then we have so-called Aldehyde reagent. This Aldehyde, phosphorus is positively charged, C is negatively charged. And then this attack here, and it forms this kind of cyclic intermediate. And the result is this whole part is removed and looks like this rearranging of a double bond on the side. And then this part is removed. And the result is CC double bond forming. In the last class, we have seen cyanide attack, and we could add one carbon addition, and then hydrolyze or reduce to make some of the product. Now, this case, carbonyl side, utilizing this CO double bond to remove it, we use the hydrogen with a strong base. Now, to make a double bond here with another carbon, this is very unique reaction and very long history reaction too. And this reaction is called as Fittig reaction. Fittig reaction, the reagent looks like attack position is here. And if you look at here, most of those cases, alkyl halide. Halide is more electronegative. Carbon side was electrodeficient. That's why it becomes electrophilic position. Right? To convert it, the trick was we added more electropositive metals, alkyl lithium or Grignard reagent, to make this carbon into negatively charged. So they act as a nucleophile. So this looks like quite similar to alkyl metal reagent. A little different, it has phosphorus as a reagent. And then if it attacks here, and then this oxygen is forming the bond with this phosphorus, and then this part is removed. This reaction, similar reactions we have seen. You have a hydroxyl. To remove that hydroxyl, what did we use? Dehydration reaction. We have one reaction. What is it? What reagent? You had hydroxyl in the mild condition. By adding this reagent, you removed the hydroxyl and generated this kind of double bond as the product. 야, 시험 지난주에 봤는데 너무 리셋이 빠른 거 아니야? Anybody? 뭐 다른 반쯤 나온 것 같아. You had a hydroxyl, and we learned several stereochemistry conversion of PBr3 and POCl3. 누가 얘기하면? Yeah. If you had POCl3, then you could remove this oxygen, and then you can generate the double bond. Seems like this is combined reagent like that. Okay. It has negatively charged carbon here, and phosphorus is nearby too. And first step is attack, generate carboxylate, and then that carboxylate, the hydroxyl is removed by this phosphorus reagent. It's similar to combine the two reagents into one. It's similar to POCl3, the mechanism. To make that reagent, you start with a alkyl halide, similar to Grignard reagent. Right? Grignard reagent, also alkyl halide, you add magnesium, metal, then metal is inserted in between, and then distribute the charges. Originally, this was a positive, this is negative. This is good electrophile. By adding metal, we changed this into negative charge. before Grignard reagent. Now Wittig found that by using this phosphorus reagent, phosphorus has a local electron. This acts as a nucleophile. It attacks this position and pushes this out. Positive charge is generated here. That means this can attract the electron, so making this proton more acidic. Here, if you add a strong base, then base can remove the proton, then this Aldehyde reagent is formed. So you can draw like a plus minus, or if this electron is donated here, then you can put PC double bond here too. That is a reagent. Okay. It may be on that relationship. This one versus the PC double bond. What's the relationship of those two? Enantiomer? Diastereomer? Is that isomer or resonance? It's a resonance because only electron is involved. Okay? That's a resonance form. So from here to the PC double bond, you can put this double head, the arrow. That's resonance. That's Aldehyde reagent. So summarizing this is a similar reaction to alkyl lithium reagent formation or Grignard reagent. But in this case, reaction is not based on the metal base. This is utilizing this nucleophile, phosphorus nucleophile attack here. Then this reaction is SN2 reaction. Right? SN2 reaction happens, and then the polarity is changed. In your textbook, I couldn't find the term, but when I learned in the textbook, it is called as a changing polarity. Umpolar. It's maybe a German word. So change that polarity from positive to negative, from electrophile to nucleophile. Okay? Then that reagent reacts with this carbon. Let's compare this reaction with a Grignard reaction. Grignard reaction with ketone, if you add the Grignard reagent, what is your product? Methyl Grignard reagent, if this attack this position, then you form alcohol generated as intermediate, right? You can form alcohol here. If you push further that reaction for dehydration, let's assume here you have one alkyl, one methyl, and then one hydroxyl. That's a tertiary alcohol, right? And then if you push that for the next step of dehydration, what would be major dehydrated product? You have two options. Double bond here, you have one of the methyl group here. So CN double bond here or double bond here. Two options, right? Which is more stable? More substrate, one is more stable. That's why if you do this reaction, this is major product and this is minor product. You have two options, just using this Grignard reagent, and here you use the POCO3. This is a dehydrating reagent. So this is the one option. If you stop here, then you can just have alcohol here, and then tertiary alcohol. Okay. Now, if you use a Grignard reagent, very cleanly, you don't get this. You get almost predominantly this product. Because of this very bulky reagent here, and then this attack here, and then this is, as I said, this one is similar to POCO3 and the function. In situ, inside the molecule, because of bulky size, it's difficult to remove this proton here. It's adding here that reacts with this proton, and then it forms this product. So if you need to make less substrate CN double bond, CC double bond, this reaction is very useful, which you cannot get from Grignard reactions. Okay. Now, there are several of the natural products can be formed. If you needed to make a CC double bond, and one side you make this Aldehyde reagent, Wittig reagent, and then the other side is a carbonyl. And then this C and this C make a double bond like that. This is vitamin A on the precursor. And to summarize this, to think about it. Now, if you have two options, double bond, one side is more substituted, and the other side is less substituted. Then, if you think about the reagent preparation, It was phosphorus plus alkyl halide. That reaction was SN2 reaction. Right? SN2 reaction is difficult to proceed with the secondary or tertiary. Tertiary is impossible, secondary is slower. So your general option is Aldehyde is this side, less substituted side. And more substituted one, more crowded one, as the other side, as the carbonate side. That is the right option. Okay. Two options to break this bond in the middle. You choose maybe this side for the Wittig reagent and this side as carbonate. That's one option too. Right? But preparing a Wittig reagent is more difficult from this side. And also to get the better product like this way, less sterically hindered side. So Wittig reagent is always the chosen as less hindered primary alkyl side. Okay. Reaction itself is very useful, but this and some other practice you can do, and even double reaction also is possible. Two sides of Aldehyde and then two reagents of aldehyde. Then the same motif can be added here and here. This is symmetric structure. The product is a keratin. The 주황색 color rectangle. Okay. Kind of reagent can be synthesized like that. So this reaction is quite useful, but as an end result, if you look at the reagent here, let's think this way. Here, if you look at those reagents, methyl group here and bromide and just one atom of metal. Molecular weight wise, maybe similar, this one, maybe one to one. Now here, and the result is just that you want to donate just one carbon, and your reagent has 3 phenyl group, 1 phosphorus. If you weigh the weight, maybe this is maybe 10 times or 20 times heavier, right? So just to deliver only 1 carbon, you need to use a lot of this reagent, and this is a highly crystalline product too. Once you make your once you finish your reaction, then you have a very white crystalline solid. Maybe you may be happy. Wow, my reaction is working very well. That crystalline solid is this byproduct. So to remove that byproduct is a lot of work and a lot of garbage you generate. You put 10 gram, you get only 0.5 gram of product, and then 9.5 gram of byproduct. So atom efficiency wise, this is not very efficient. So chemists wanted to try to modify and replace this reagent. But historically, this Wittig reaction is very clean and a very unique product you can get. So if you can find alternative method, not using this heavy reagent, light reagent, the lightest reagent may be electron. So that's why maybe the electron-based chemistry, electrochemistry may be very popular way. Then no other byproduct can form. Only water and just electron may be better way. But anyway, historically very important one, and you can compare this as reference. Okay, you may practice with some of the problem. So let's summarize of nucleophilic addition to the carbonate. We have carbonate. It can be ester, it can be ketone, it can be aldehyde, kind of carbon group here. We have a nucleophile. Nucleophile attack first, 75 degrees from this way, right? Not from the same plane. Once it is attacked, it forms sp3 tetrahedral intermediate. Now, next option is this electron can be pushed back, and then it has 3 options to break the bond if it comes back. If this is once it forms the tetrahedral, geometrically it's the same for all of the 3, right? And then if it comes back, it can push original one nucleophile side clip, then it goes back. If it removes one of these leaving group, then it forms the product. Or even it can break maybe this bond. And this reagent, let's say, if this is a good leaving group, then the reaction moves to the next step. But if that is alkyl or hydrogen, usually that reaction is quite slow. But exceptionally, if that reaction, if there is an acceptor nearby, let's say this is aldehyde, hydroxide attack, then it forms this kind of intermediate, and 2 hydroxide in both sides, right? And if this is pushes back, easily maybe this water can be removed, it can go back from the original side, but very small portions. This hydride can be removed too if there is a nearby reactant. Then this hydride can attack here. Then one side is oxidized, the other side is reduced. It's funny. This is in the middle, right? Aldehyde is in the middle. This is fully oxidized. This is fully reduced. Sometimes we try to make this into this, or this into this that we didn't want it, and this into this. But funny thing is, 2 intermediate states. One goes to oxidized product, one goes to reduced product. Not very common other reaction. Cannizzaro other reaction discovered by that chemist maybe. But if it happens, if that donor and receiver is very nearby. So if this is attacked, and hydride can attack directly this one, then one side can be oxidized and one side can be reduced. It is observed, and then it seems like a similar reactions is occurring in nature too. You may have heard at least these names of the natural product. NADH as a reducing reagent. NAD plus is oxidized form. So this can be reduced to this. That the reduction happens by this kind of push and hydride generations. This hydride is not free hydride. It's similar to the previous case. In situ generated hydride only when the receiving partner is nearby or oriented properly by enzyme. Then this hydride can be donated here. Then this is oxidized form. And other hydride can come back and regenerate the NADH. So the balance of NADH and NAD plus in the body is quite important. More NADH usually considered as healthier condition. We want to have a more reducing reagent than oxidizing reagent. Oxidizing reagent always we hear antioxidant. Antioxidant is considered as a good material. We want to suppress oxidation. This is one of those anti-oxidizing reagent, reducing reagent. Okay, one more on the concentration for carbonyl addition. Now, if you have this carbonyl nucleophile, attack here, first product is a hydroxyl. To remove that hydroxyl, POCO3, dehydration, that's the next step. But first reaction product is by adding nucleophile and hydroxyl group is formed. Okay. This is what we call 1,2 addition. Why 1,2? We can compare it later. And it is conjugated. It's a little different situation. Now, carbonyl and then conjugated like this. Then, electron density wise, this one is a negative, this one is a positive. If this 5 electron is moved around, we have seen the 5 electron donating effect is 1 carbon alternatively to the next one. So if this is pushed there, then this is negative, positive, negative, positive. So this conjugated system has a similar the property of this carbon and this carbon, both of them are electron deficient. Then nucleophile has chance to attack either here or here. And numbering, if you have any functional group like a carbonyl, usually what we call the next one as an alpha position. This is a beta position. But numbering wise, funny way, we always put number 1 for that position, this carbon. This is a 1 position, 2 position, sorry. Here we use the numbering 1, 2, 3, 4 position. For this case, 1 position and 1 position of the case to explain it. So if nucleophile is attacked here, then the intermediate is this kind of an enol form. Right? Enol form can be rearranged into this ketone form. So end product, end result is like this. And nucleophile is added here. And comparing to 1,2 additions, 1,2 addition is here to here. This is 1, 2, the position here. Okay, anyway, this is 1, 2 position. If it's nucleophile attack here, then product is formed here. This is what we call 1, 2 edit product. If this react here, then the end result is 1 to 4 position. So this is called as a 1, 4 addition product. What is added? Nucleophile is added, and proton is the added here. That proton, 1, 2 addition, that proton is added to this oxygen. In this case, that proton is added here. And the result wise, seems like this is added like this format. 1, 2 position. Here, 1 nucleophile to this position, 1, 4 addition. So these two option is possible if we have this kind of conjugated system. Okay. Now, what's the difference between this carbon and this carbon? To selectively attack either 1, 2 position or the 1, 4 position, this carbon is directly attached to the oxygen. Oxygen is very aggressively attracting the electron, and it's very nearby. Electron is more pushed this way. It's kind of a shrink, it's more, maybe this bond is shorter. In comparison, this CC bond is a little remote, even though this is delta plus, but this bond is a little more flexible. So then people say, chemists say, this one is more hard position, more compact position. This one is a little more soft position. More electron density wise, a little more flexible position. So if you choose nucleophile as a hard one and soft one, then we can have some controls. So here, if you look at here, this is the explanation of it. This is a positive, negative, positive. Alternatively, the different position. Now, if it is just a CC bond evenly distributed, and there is no electrophilic positions. CC bond is usually acted as electron donating part, not electrophile. In this case, because of this carbonyl attracting effect, nucleophile has a chance to either attack here or here. And if you look at here, with this unsaturated the ketone, here we have amine. Previously, if that was a simple ketone, it attacked here and it formed imine. Right? That was the product, that's a 1, 2 product. And that was the only product we could expect. But in this case, there are two options. This can attack either here or here. And the product is, if it forms 1, 2 position, this is the product. Now this one is bothered by this extra extended deconjugated the electron. That's why this is not so stable. And then whole of those processes are all in equilibrium. They move to this direction and coming back. And the most stable of the form out of all forms, this is most stable form. Negative, positive, and proton is shifted here. This is most stable form. That's why if you have the alpha beta unsaturated carbonate with the amine group, only 1, 4 product is the dominant product. 1, 2 product maybe the temporarily can be formed, but can shift to go back to the 1, 4 product. Okay. Amine added to alpha beta unsaturated the ketone, it forms the 1, 4 product. Other options. Carboanion. We have learned several different carboanion today so far. Fitting reagent is one of them, or metal reagent. Grignard reagent or lithium reagent. They are hard reagent. Small hard metal is added. That carbon is a hard, small denucleophile. They prefer to go to CO attack here, 1, 2 position. Then, how to make that reagent into more softer carbon? The trick was generated this way. The making lithium reagent or magnesium the reagent, Grignard reagent is similar. I can highlight and we add metal powder. Then it forms this R minus or RNGX reagent. This is a hard nucleophile, and once you make this the lithium reagent, you further add soft, heavy metal halide, copper halide. Then they exchange and to form this kind of reagent. Material balance wise, it looks the same, just mixed with alkyl lithium with copper iodide. All together, if you just count, it looks like it's the same. But if you look at the inside, directly contact side of this alkyl group, originally it was connected to lithium. That's why it was highly compacted, tight, hard nucleophile. And this one was exchanged with the copper. Copper is inserted here, push out to the lithium. Lithium is now existing outside just to keep the charge balance. The real reagent is alkyl is directly connected to copper. Copper is much bigger and has a lot more electrons. The electron shell is also softer and complicated, the d orbitals. And these are the alkyl group is now it's more relaxed anion and a little more softer anion. So by using this trick, making this hard alkyl group, hard alkyl anion into soft alkyl anion by exchanging the metals. Lithium, magnesium, hard, small. Copper is relatively bigger. Of course, chemists has tried many metals here, especially even until today, the organometallic chemists, they tried all the metals. We have maybe almost hundreds different kinds of metals in here at the table. So far, one of the successful cases is this copper reagent, so-called cuprate. Now, by using this trick, now we can control. We have this starting material. If you wanted to attack 1,2 position here, then with the methyl grenade reagent or methyl lithium reagent, act as almost a similar. Attack this position and just catch it. Okay? Then we can get this 1,2 product. Addition, nucleophile, and the proton was added. Now, by changing this into copper reagent, this reagent by adding copper iodide, now this becomes soft nucleophile and it prefers to attack 4 position. And then push this up and then end the product is this. Okay. Yeah, explanation. So copper reagent case it attacks 4 position and then this one is the anode form is changed into ketone form and then finish up the reactions. How to make this reagent, this product? If it was 1,2 position, then your product is hydroxyl on this position. Now this is carbonate. Then you need to imagine that your reagent was maybe double bonded here. And then reagent should be this one will interact with this double bond, alpha beta unsaturated double bond. And your option is either lithium, magnesium, or copper. Then you need to have soft one, and in this case you add this copper reagent. And then utilize this, then attack here and finish it. Okay, some of the practice problems from the textbook and study further. Okay, earlier spectroscopic the part. In IR, now this is the first time to see carbonyl, but in a sense, IR most useful information is a carbonyl signal, right? Fading the strong signal around here, 1,700, 1,700 range. This is carbonated. IR gives you some partial functional information. So either it has a carbonyl or aldehyde, 200, the 2,800 range, a little sharp, but half of the intensity. But most apparent one is carbonyl, strongest one. And water hydroxyl is a little broad, above 3,000 around here. And other than that, it's quite difficult to utilize those informations other than you use AI. And with the AI, you can look at this fingerprint area that you can compare this different spectrum. That's one option. But as a chemist, by looking at that spectrum, your first thing you want to see from IR is whether it has a carbonyl or not, and aldehyde or not. That's almost the dominating information you can get from IR. And if you look at here, depending on aldehyde, amide, ketone, slightly changes, but all about 1700 range, very strong peak. That's CO double bond peak. NMR. NMR wise, aldehyde is quite unique. CHO position, that's among the functional groups. Usually that's most downfield to peak. Explanation is kind of some benzene-like the ring current kind of thing, but it doesn't matter. Anyway, aldehyde peak is around 10. It's quite uniquely most downfield peak. When it has proton is attached to carbon with a 1 heteroatom, no heteroatom is about 1 to 2 range. 1 heteroatom, it becomes a little above 3 to 4. If it is attached to carbonyl's electron withdrawing effect is a little less than heteroatom, like the halogen or oxygen. That's why alpha position of a carbonyl is about 2. So those are two informations. Aldehyde around 10. Alpha position of a carbonyl is about 2. Heteroatom about 3. Okay, let's add up the kind of information one by one. And in carbon, also carbonyl is quite unique. It's also the most downfield shifted one, about 200 ppm. Carbonyl or carboxylase, the aldehyde, ketone, or any other the carbonyl other reagent gives you most the downfield shifted the one about 200. Okay. Okay, this mass spectroscopy. 이 페이지 보고 불편해야 되는데 불편하라고 썼는데 이렇게 쓰면 안 되잖아, 그지? mass spectrometry. 여기는 빛을 사용하지 않았기 때문에 다른 경우는 IR도 빛을 사용했고 NMR도 마이크로웨이브를 사용했고 다 일렉트로마그네틱 웨이브가 들어갔기 때문에 스펙트로스코피라고 해요. 여기서는 그런 게 없었기 때문에 in mass spectrometry, if it has a carbonyl group, it has once we have this kind of ionized, and then there is a different fragment pattern, and they generate this kind of alpha beta again. This carbonyl is centered, and this alpha beta gamma position. Right? So one position was onto beta position attack. Right? And fragmentation can happen. It can generate this kind of fragment here with one alpha carbon, or alpha cleavage is also possible. Cleave here or cleave here. If this is cleaved, this is plus dot means one electron was removed. It's a radical and positively charged. If this is break up here, R dot and then this positively charged, which one can you see in mass spec? R dot or this carbonyl? In mass spec, you start with this, and if there is a breakdown like this, it generates one radical and one the cation. Then which one can you see? Radical or cation? 내가 질문을 잘 못하고 있는 건가? 배우니? 조혜요? 여기서. Which one can you see? 내가 무슨 질문을 하고 있는지를 잘 캐치 못하면 in mass spec, you cannot see neutral species. It doesn't matter whether it's a radical or molecule. In mass spec, only you can see charged species, either negatively charged or positively charged. The basic mechanism of mass spec is charged particle travels in magnetic field. Then it has force to move this kind of circular motion. That is the mechanism. That's why to get mass data, you need to ionize your molecules. either negatively charged, positively charged. Positive charges travel this way, negatively charged travel this way. Only with that difference, and then this angle and distance can give you the information of molecular weight. Okay, that's why in this case only you can see this part. So as an end result, any carbonyl molecules, you have alpha cleaved product like this, or alpha beta cleaved here. This kind of a material, this kind of a fragment you can see. Then you can get an idea whether it has carbonyl molecule or not, and how big is the alkyl group here by looking at this necessary. It takes a little of the practice to figure this out, but anyway, this is the basic information for carbonyl compound. Okay, asymmetric synthesis. This part is not in your notebook, I guess. Here, if you have this reagent, proxy acid, MCPDA was one example. MCPDA is added to double bond, then it can form epoxide reagent. Now, depending on those sides, whether it's from the top or from the bottom, it can form two results, up and down. So it's time to time it's very difficult to control. There is no chiral material here, no chiral. Then best result you can expect is half and half as a racemic mixture. And by adding this kind of catalyst, then chiral catalyst, then you have a chance to get only one product than the other. This catalyst generates the chiral environment. When it is added, it's preferred only one side than the other. This kind of synthesis we call it's not symmetric. That's what we call it asymmetric synthesis. Do you know who got the Nobel Prize this year? Chemistry. Nobel Prize was given this to 3 people. One of them, history is very Sharpless. He got the Nobel Prize of asymmetric synthesis 20 years ago. And he got the Nobel Prize again this year. Maybe this is the second case of a double Nobel Prize in chemistry. There are several other scientists who got the Nobel Prize, like Linus Pauling. He got one chemistry Nobel Prize. Second one is Peace Nobel Prize. But this is second case. You may figure out who was the first one. Anyway, his previous work was asymmetric synthesis. He got one Nobel Prize. But this year, they generated another Nobel Prize with a different topic, so-called click chemistry. Why click? Why is it named as a click? It's your mouse clicking click. Mouse click is easy, right? So it's like as easy as just click your mouse. Any reaction it can work with this chemistry is the topic of the Nobel Prize of this year. Okay, when I gave you the quiz in the beginning, and then your name suggests that there may be some typical time for next week, and I looked at the schedule and whether 수업 진도 안 빼먹고도 할 수 있을까 그러다 보니까 스케줄 잡을 때 한 주 정도 서머리하고 리뷰하는 세션을 넣어놨어. 지금 정도 하는 걸로 봐서는 한 주에 한 챕터씩 하는 거 크게 무리는 안 되는 거 같고 할 수 있을 것 같아. 그래서 이거 안 빼먹고도 한 주씩 밀면 그러면 다음 주는 저런 걸로 대체하는 건 어떨까? 클리킹리스로 수업을 한다는 얘기인 거예요? 재미없는데 이것저것 생각을 해봤는데 그래서 다음 주는 중간고사가 있는 주니까 화요일하고 목요일 하는 수업은 하지 않는 걸로 여러분들은 중간고사에 좀 더 포커스를 하는 걸로 그래도 한 주를 통째로 다 비기는 좀 그러니까 오늘 내가 숙제를 줄 거니까 이번 주에 배운 내용은 다음 주 화요일까지 미루지 말고 더블반드만 들어갔는데도 꽤 뭐가 복잡한 얘기를 새로 있는 것 같잖아. 정리를 미리 하는 게 좋아. 다음 주 화요일까지 숙제는 내주고 미리 하든지 뭐 어떻게 하든지 숙제는 내주고 대신에 다음 주에 플리캠스 공부를 하는데 공부할 수 있는 한 가지 옵션은 다음 주 수요일 저녁에 학과에서 알아두면 쓸모있는 노벨 박상 이런 거를 6시에 1시간 반 정도 올해 노벨상에 대해서 소개하는 노력을 하는 것 같은데 거기 가서 참석해서 듣고 공부를 해도 좋고 혼자 공부해도 좋아. 그리고 숙제는 그 다음 주 화요일까지 양이건 뭐 이런 건 다 관계없고 클리켄스가 뭔지, 왜 중요한지, 올해 왜 그게 노벨상을 받으면 했는지 한글로 써도 좋고 손으로 써도 좋고 뭐 뭘 해도 좋고 해서 리포트를 그 다음 주 화요일 날 숙제 내듯이 같은 날 내는 걸로 다음 주 스케줄을 대체할게요. 절대로 이렇게 하면 안 됩니다. 만드는 사람 없으면 이렇게 가보도록 할게요. 이 뒷부분 얘기는 내가 두 버전을 만들어 왔는데 별로 원하는 사람이 많지 않으면 그냥 수업하는 걸로 그냥 노트를 하나 만들어 왔고, 그래서 이 노트 뒷부분 요약해서 수업 마치고 내가 올려줄 테니까 이거 보고 이 스케줄을 하면 되겠습니다. 그러면 다음 주에는 나와보는 수업은 없고 이걸 참석하는 건 옵션이야. 알아서 하시고 공부해서 리포트 하나 내는 걸로 한 페이지짜리 좋고 뭐 어떻게든 하여튼 키 컨셉이 들어가게 저 공부했어요. 그리고 이런 걸로 정리했어요. 같은 토픽으로 올렸으니까 그거 가지고 뭐 또 컴피티션 해서 컨테스트 해서 또 상주기 해보든지. 오케이. 그래서 스케줄 약간 바꾼 게 이렇게 다음 주에는 올해 노벨상에 대한 거 약간 공부하는 거 그거 대체하고 조금 가벼운 부담으로 그 다음 주에 다시 돌아와서 화요일부터 가르는 얘기로 다시 돌아와. 그래서 다음 주에 갔다 와도 문제 없지? 다음 주에 신체 공사해야 된다고? 다른 학생들하고 붙어서 이길 수 있어? 꼭 잘하고 와. 오케이. 그래서 수업은 여기까지 하고 질문 있으면 질문 받겠습니다. 잠깐 하기 전에 해줄 거 하나 있으면 맘빨리 해볼 때.